Um, okay, so today I have the honor of hosting a talk by Tom Jordan from the British Antarctic Survey in Cambridge, and he will be sharing his latest research findings on the fascinating Thwaites Glacier and how airborne gravity, magnetic, and radar data can help us to better understand the subglacial properties. So without further ado, I'll hand over the stage to you, Tom.
Thank you very much. I'll just start my presentation. So yes, I decided, well, I was asked to talk about the paper I've done recently, which was producing a geological sketch map of the Thwaites Glacier um, from various geophysical sort of observations. And before I start, I'd like to thank Ben Kalesa, Sarah Thompson, and Fausto Ferraccioli, who've all helped me out with this paper and helped kind of inform the background of the sort of glaciology and the tectonics and do some of the modelling. So yes, thanks to all of those guys as well. So yes, this work is a contribution to the International Thwaites Glacier Collaboration (ITGC), which I'm presuming that everybody on this meeting has heard of. If not, I'm not quite sure why. We should be trying harder in our media department. But why was Thwaites really important? It's thinning and having a direct impact on global sea level now, but the future trajectory of the glacier is unclear. And the underlying geology is really important for the ice dynamics, but also for understanding of the tectonics of this region. And Thwaites Glacier lies quite close to the sort of transition between the Antarctic Peninsula, which is one kind of tectonic system, and the West Antarctic Rift system, which is a separate but linked tectonic system. So this area is of interest both from a tectonic perspective and from a glaciological perspective. And the paper is out in Science Advances. But the thing I wanted to stress is the data for the geological sketch map, the line work for it's available from the UK Polar Data Centre. So if you want to plot up my map and argue with the interpretations, that's the place to get the actual line data if you want to plot it up. So how did we go about creating a geological sketch map? Well, the area's actually got relatively good data coverage. We've been studying this area back from 2004 through till the last data for this project was collected in 2019 from various different national and international programs. Not all programs collected all kinds of data. So, for example, Operation Icebridge, which has got red lines with fantastic high resolution data coverage, didn't have magnetic data on board. So some of the geological interpretations are kind of limited by lack of data in places. But these were the input geophysical data sets, and primarily radar, gravity, and magnetics. And the thing to stress of why we're doing this with geophysics is that it's almost zero rock exposure. And the rocks that are exposed are quite often recent volcanics, localized around volcanic centers, which means that they're not likely to be representative of the broad scale subglacial geology in the area. So this is where we turn to the geophysics to try and work out what's underneath. So how do we go about doing this? So working through the various different data sets, the first data set was the airborne radar, which gives us the subglacial topography. And the map, just to stress, is the blue, brown, greeny transition is at minus 750 meters, just because that gives me a nice color scale that shows up the coastal sill quite nicely, even though it's at that, what you think is the sea level transition, that's still 750 meters below sea level. And this slide shows up why Thwaites is at risk, because it gets deeper and deeper as you go into the deep basins in the background, which puts it at risk of marine ice sheet instability. The other thing we could get from the radar data was the roughness of the bed. And we did this by looking at a 1 kilometer moving window along every radar flight line. And within that 1 kilometer moving window, we calculated the standard deviation of the bed elevation. So where the bed is very, 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 very smooth, the standard deviation is very low. Where it's very rough, obviously the standard deviation of the bed within that window is very high. And from this, the basic sort of first takeaway is there are three main provinces in the Thwaites region. There's this upstream area, I call a incised highlands. It sort of looks like a feudal system, very deep, narrow, U-shaped kind of valleys, and comes out very, very rough in the roughness calculation. Then we've got this downstream area, which I call the eroded lowlands, and they're much, much smoother than the highlands, but they're not the smoothest. So you look at the radar profiles and you can see that there is clearly topography along the radar lines. And it looks like essentially you've taken away an awful lot of that sort of feudal topography and just wiped it out. But then there's a third kind of area, these very, very smooth areas outlined in yellow, and I call these residual basins. And so those are sort of three geomorphic regions that we pick out from the roughness. But that just sort of tells you about the ice bed interface. It doesn't really tell you about that much necessarily about the deeper geology. So this is where we turn to the potential field, the gravity and magnetic data. So first, looking at the gravity data, we have the free air compilation, and this is the sort of first processed data that you get off the aircraft. And the first thing that you show, if you compare that to the topography, it matches really nicely. So gravity pointless. No, slight joke. The free air gravity signal is dominated by the subglacial topography. That subglacial topography is the biggest signal in the free air gravity anomaly. But because we've got the corresponding radar, we know what the topography is, and we can calculate what the gravity effect is and subtract that out, that sort of interface signature out, which gives us an ability to look at the deeper geology. The first step is the Bouguer correction, where we stripped out that topography. And as you can see, the high frequency correlation with the topography, it isn't present anymore. But you do see a broad correspondence between very deep, or the deeper basins and positive values, and the higher topography and negative values. And this is due to isostatic compensation, where high topography has a low density crustal root or some form of low density material at depth that's actually supporting it. And to get rid of that signature, because we're trying to look at what the shallow geology is here, we don't want what the crustal thickness signature is. We calculated an area isostatic model, which you can subtract from the Bouguer anomaly to give the area isostatic residual, which is theoretically just those high frequency gravity anomalies due to density contrast in the upper crust. And I stress we use an area model because it's a very quick way to calculate the isostatic compensation and the gravity effect of it. Other forms of isostatic compensation are available, but the gravity effect of, for example, warm mantle plume bringing low density mantle material holding up Murray Birdland would also give an isostatic response. But the gravity effect of that would be very similar to a crustal root supporting the topography. So we just use the area model as a quick shorthand to get us rapidly to the anomalies that are due to the shallow geology. And looking at this map, the first thing that we can see is that there is, parallel to the coast, a set of approximately linear gravity anomalies, which are quite distinctive, and they've actually been noted way back in the 2004 publications of Teresa Damiani and others, noted that there was probably going to be this signature showing up at the mouth of Thwaites Glacier. So moving on to the next data set that we've got the magnetic data. So this is a compilation of all those data sets that I showed previously. And we did some digital enhancements. So here you can just see highs and lows, but using an enhancement called TDX, this shows up where the edges of the theoretical source bodies would be. And those are sort of colored, shaded as dark lines in the digitally enhanced map. So this is a map of where the edges of all the geological source bodies is. So this is starting to be step one of a geological map, because this is the edge of all our geological bodies according to the magnetic data. So now we've got our, oh yeah, and very tellingly, you can see this very similar set of linear bodies lining up parallel to the coastline of Thwaites Glacier, suggesting that the signature that we're seeing in the gravity is also from sources that are affecting the magnetics as well. And we've got this secondary set, which we didn't really see in the gravity, coming in at 90 degrees, showing that there's like a more complicated gravity signature in this region. Using the magnetic data, we can also do depth to source analysis. And we did two different varieties. We did a tilt angle, which shows up the source, the depth of the edges of the sources. And we did a 3D Euler analysis, which gives us slightly more distributed view of the source depths. A magnetic depth to source is, you have to make a lot of assumptions to do the calculations, and noise can drift into the data and blur the picture. So depth to source is only ever going to be a first approximation. But what both of these techniques seem to be showing is generally the sources are at depths beneath the bed of 0 to 1 kilometre, so fairly shallow. It isn't a vast sediment-filled basin with 3 to 5 kilometres of non-magnetic sediment. That could be present if it was full of highly magnetic volcanic material or something like that. But the first past impression is there's a lot of magnetic sources relatively close to the ice bed interface, right the way across the Thwaites Glacier region, which differs from some of the other Cycle Coast or Institute Muller going into the Weddell Sea areas, which we've looked at in the past. So zooming in, looking at these two magnetic anomalies close to the coast, we did some 2D depth source analysis and also produced some 2D forward models. So this is showing those models. The upper panel is the magnetic anomaly, and the fit shown is in black. And the second panel is the airy isostatic gravity anomaly, and again the fit in black. And then you can see the magnetic susceptibility with the depth of source crustal section and the density crustal section beneath. And the main thing to stress here is basically we can recreate the magnetic and the gravity anomalies with the same bodies with distinct density and susceptibility values. So these models show that it's a pretty valid conclusion that the magnetic and gravity anomalies have joint sources. So the body that's creating the magnetic anomaly is creating the gravity anomaly. The positive gravity anomaly as well is perfectly plausible with this modeling. And we used the magnetic depth to source as a rough guide. And you can see that many of the different techniques show a lot of scatter, but also that they are coming together in clusters, which agree between the 2D and 3D methods. And when we use these for our model to guide our modeling, the model works out relatively well. We also did some 3D inversion, focusing in again on the same area to try and understand these bodies a bit further. This is the inversion result. It was a distinct inversion where we inverted the magnetics or inverted the gravity, but both cases they seem to show up these linear bodies at approximately the same depth, although the output of the gravity appears to be more noisy, and we couldn't get the same resolution and get a successful inversion. And one of the outcomes of this is it suggests that this high susceptibility body shown in red in that figure A contributes about 12% of the upper 12 kilometers of the crust. So that is a really significant volume of the crust is made up of this high susceptibility material. And you can see when you plot the sections and compare them to the forward modelling that's sort of done by human, that the high density and high susceptibility bodies are sitting within the same, approximately within the same volumes, which gives us some kind of sanity check on both the human version and on the inversion. But both are kind of giving a broadly coherent solution. So we've looked at our data. We've done some geological modelling that suggests we've got these joint sources close to the grounding line. So how do we actually go about turning this information, these ideas, into a geological sketch? Well, first, so we've got these signatures: topography, gravity, and magnetics. And working through each of these sets of signatures, groupings of signatures start to give us an idea of what the geology is. So starting with the very smooth basins, the topography is really, really smooth. They're associated quite often with negative gravity anomalies, but there wasn't really a magnetic signature. And our interpretation of this is these are relatively thick sedimentary basins. And when we zoom in to an area, on this figure, I've contoured up so that this figure here on the left, the standard deviation, that's bed roughness. But overlain on it in contours is the area static gravity anomaly. So this is calculated completely independently, and you can see that the contours, the negatives, close nicely within the really smooth regions, which is where we think, okay, so you've got a low density body, the surface is really smooth, which suggests it's relatively soft and easily deformable. This is pointing us towards these being sedimentary basins. And when we look at the swath radar that was collected in like a little high resolution patch, you can see that within the what we are interpreting as sedimentary basins with a smooth bed, you see these megascale glacial lineations, which is really typical in the offshore record of areas where you've got thick sediments, and that's where you get these lineations forming. Downstream, where you've got rougher bed and outside the sedimentary basin, this is where you get canyons and sort of a much more rugged topography, which in offshore regions would be interpreted as exposed crystalline bedrock. So this is our first geological body. These are the sedimentary blocks. I would stress this one slightly further downstream that I've not shown the figure of. That corresponds to a gravity high, but it also overlies one of these major bands at the mouth of Thwaites Glacier. And I think you've got a superposition of signatures where you've got a sedimentary basin shown up by the smooth bed overlying a dense body, which is messing with our signature. So what about the next set? Yes. So yeah, we've got some sedimentary basins. What's their age and origin? Well, the gravity data suggests, just a back of envelope calculation from that negative anomaly, suggests they're about 1 kilometre thick. So it's not just a thin drape of till in these areas, you actually have a thick sedimentary body. It looks like they're low density and relatively easy to deform. So it's not already deformed, high-grade metamorphic rocks that you might associate it with a convergent margin. The convergent margin was present here until about 115 million years. So we think these rocks likely postdate that convergent margin. The basins lie parallel to the rifted margin. So this sort of, it wouldn't be unreasonable to suggest they are a part of the rifted fabric, and that rift developed around 100 million years ago. And also offshore, they've drilled sediments, and these are associated with Cretaceous rifting. And these Cretaceous sediments directly overlie the crystalline bedrock. So that pattern of a sediment abutting a crystalline bedrock would be what we're thinking is happening in these basins inboard. So we think a Cretaceous age for these basins is most likely. An alternative Eocene, Oligocene, transtensional setting where the West Antarctic crust was moving east-west, but that's parallel to the basins, and that seems to be a little bit more of a complicated setting compared to just a simple extensional model. But it remains an option. So the next area we look at is these bodies here outlined in green. They don't really show a clear topographic signature. They do show strong positive and gravity and magnetic anomalies. And again, I've overlain the magnetics at the top with the contour of the areostatic gravity anomalies, and you can see the highs pretty much overlie the highs in the mag. And I've done the reverse at the bottom, where the black outlines are the outlines of the mag sources from that TDX calculation. And you can see that those magnetic outlines enclose quite nicely the gravity highs. So that's the signature we're looking for, and that's the distribution on the main map is where we think we've got the mafic rocks. And the reason we think they're mafic is because they're dense and highly magnetic. That kind of coupled signature of a dense, highly magnetic rock would be pretty typical of a mafic rock. So what's the age and origin of these? Well, again, they're parallel to the rifted margin, which, that points quite well to being a rift origin. Offshore, the dominant detrital age is about 100 million years. So something underneath there is 100 million years old. And these are quite big blocks of rock, so that would be maybe a good age for them. Similar amplitude and orientation offshore magnetic anomalies in the Amundsen Sea embayment have been linked to Cretaceous rifting by other authors. So other people obviously think this is a reasonable interpretation. And then on New Zealand, the conjugate margin, it shows similar anomalies, and these have been dated from some remote islands to about 84 million years. So this, although the ages don't precisely agree, the sort of setting of rift, a highly magmatic rift during breakup between New Zealand and West Antarctica seems to be fairly consistent on both sides of the conjugate margin. So we think these are a Cretaceous feature. Then the other, but there is an alternative, as always. Down at Mount Murphy, there's exposed gabbro, mafic, highly magnetic, at 34 million years old. And it could be that all of these rocks further up across the Thwaites catchment are 34 million years, but that doesn't correspond with the dominant age coming from the sediments offshore. And it's also interesting that the Mount Murphy gabbro shows an incredibly strong 2000 nanotesla magnetic negative because it's got a really strong remnant field. And we don't seem to be seeing that over the main trunk of Thwaites Glacier. So we prefer this Cretaceous origin. So moving on to the next rock type, we're calling it an intermediate rock type. So this isn't strongly mafic, like a dense rock, or strongly acidic, a relatively low density rock, because we don't actually see any gravity anomalies, clear gravity anomalies associated with these magnetic anomalies. So the only thing that's showing up that these are a distinct rock type are the magnetic anomalies. So the underlying rock type must have a relatively neutral density relative to the rocks on either side. The age and origin of these, it really is very unclear. They could be pre-rift associated with the subducting margin. They could be a post-rift, and you can see some of them seem to lie around Mount Takahe, which we know that's a recently active volcano, so it could be associated with that. Or it could be a combination of both in different areas. We just don't know. So finally, the last of our geological bodies, these are granitic bodies. Acidic geochemistry, so they're relatively low density. And the reason we're interpreting the key signatures is their high topography, but a negative gravity anomaly, but there's no clear magnetic signature associated with any of these bodies. And this is just an example adjacent to Pine Island Glacier, where these highlands that show up gravity negative 1, GN1, the highlands show up as strong negative. That suggests you've got something relatively low density, but that's resisting erosion really, really quite nicely. And that would be work quite nicely with the granite, which are known from other areas where they outcrop through the ice sheet. The granites will form subglacial highlands. So highlands that are formed by a low density material look like they could be good candidates to be granites. And then these are the smaller inboard bodies where you can again see corresponding negatives and topographic highs. So what's the age and origin of these? Well, it's been suggested that there's the New Zealand batholith about 150 million years just prior to rifting. You had this big pulse of arc magmatism and associated batholiths forming right through New Zealand. It continues through Antarctica, and it defined the Amundsen sector and the Ross sector, with the Ross sector being the Amundsen sector being dominated by this medium batholith magmatism. And you can see that the Pine Island Glacier and outboard of Pine Island Glacier, we've got on some of the islands granites exposed, which are consistent with this Amundsen sector. It's only a minor rerouting of where this boundary has been drawn based on some rock outcrop at Mount Murphy to put it this Pine Island Glacier large granite as part of the medium batholith. These other granites are quite a long way inboard from where we think the Amundsen sector is. So it's unlikely they are part of the medium batholith. So it makes it a bit more complicated. They could be anorogenic granites associated with rifting, similar to Gedworth Peninsula further south, the other side of Murray Birdland, or potentially they could be older pre-rift granites, similar to the New Zealand Paramia suite. So these are late Devonian to late Carboniferous age granites. These were associated with the very, quite far pre-rift subduction system. So that is our geological sketch that we have created. And it pulls together all these different strands. And I think it can definitely be argued with about the ages and precise interpretations of a lot of this. But broadly, I think the boundaries of the features that we're seeing are going to remain robust with time. And the next bit, I'll just give a bit of a discussion of the implications of some of these features for the ice flow, and then finish up talking a little bit about heat flow, which I know there's a particular interest in this group. So the first thing to note, the sediment distribution is restricted in Thwaites Glacier, and this goes, I think, quite a long way to explaining why Thwaites surface slope is so much steeper than the Cycle Coast or Institute regions. And this was noted back in like 2012. You can see the Weddell Sea and Cycle Coast, very low profile glaciers. Both of these are flowing out, areas flowing out over big, thick sedimentary basins. The Amundsen Pine Island Thwaites Glacier, it probably isn't. It's probably flowing out over much more rugged crystalline bedrock. It doesn't have this thick sedimentary basin. And the point of this is actually, we can't resolve with the geophysics whether or not there is a thin skin of till draping up this whole region. But what it seems to suggest is that you need the big, thick sedimentary basin to provide the till and allow really fast flow, whereas if on a low profile flow, whereas if you don't have that thick underlying sedimentary basin, you can't get that type of flow. And that next point is about subglacial water. If this interpretation that there isn't thick sedimentary basins present, that means the water, you're not going to have big areas of groundwater flow acting as a conduit of water out to the ocean. So any subglacial water is likely focused at the ice bed interface rather than the subglacial aquifer. So that's something we're going to have to look at, of how the water flows at that ice bed interface. And yes, I think a sedimentary veneer over some of the highlands is possible, but only the thick sedimentary basin allows you to get that smooth, low drag bed in the long term. But I think there's, in addition to the sedimentary basins, I think there's a direct coupling between the geological structures and the glaciology. So it's not just, oh, we've got sedimentary basins, it's fast flow, anything else it's not. If you look in more detail, this is a recent inversion of basal shear stress done entirely independently of me, which is why I quite like the figure. When you plot the geological boundaries, yes, you do see that the sedimentary basins are associated with really low basal shear stress. But the pattern of the basal shear stress you see further downstream seems to correlate with the margins of the geological bodies we're identifying outside of the sedimentary basins. So it looks like those geological contacts between different rock types are having a direct impact on ice flow. So this suggests faults juxtaposing different rock types, or water coming up faults, or things like that might actually be influencing the flow of the glacier. And then moving on to the heat flux idea and what this means for heat flux. The subglacial geology, we think those mafic bodies are likely associated with Cretaceous rifting. We think the sedimentary basins are also associated with Cretaceous rifting. And this means that elevated geothermal heat flux, although possible, shouldn't be assumed. And I've seen it in papers quite often. The West Antarctic rift system, where geothermal fluxes are expected to be high, this tectonic setting of the ice is likely to favour relatively high geothermal heat flux. And a lot of this seems to be based on the paradigm that, oh, it's rifted, oh, it must have high heat flux. And that I don't think is true. So this is just a very, very simple back of the envelope model where you've got at sort of time one, you've got crust and lithosphere. You rift that crust and you thin it and you upwell the convecting asthenosphere, you bring hot lithospheric mantle much nearer the surface and you get high heat flux. But then over time, this lithospheric anomaly will cool and you'll end up back down with the convecting asthenosphere at the same depth and the lithospheric mantle at the same thickness, but you've actually reduced the thickness of the crust, and the crust is producing about 50% of your heat at the surface. So you've thinned the crust by 50%. So you've actually reduced the total, a long time after rifting, you've reduced the total heat flux. And you can sort of do some fairly simple one-dimensional calculations. And so at T1, you've got crust 35 kilometers thick, and you rift it down to 20 kilometers, and you get this red curve shows the spike in geothermal heat flux as that hot lithosphere is affected towards the surface, and you get a really big spike in heat flux. And then as time goes on and that thermal anomaly relaxes, as you see in the oceans, where the oceans get deeper away from the ridges due to relaxing thermal anomaly, that thermal anomaly actually goes below what it was prior to rifting. So if you had a Cretaceous rift, it suggests that geothermal heat flux of the area should be relatively low compared to an unrifted region, which is quite an unexpected result. Conversely, of course, if you had Cenozoic rifting, geothermal heat flux of this area would be high. And I did some back of the envelope calculations many years ago. They were never published, but it was working on Pine Island glacier catchment, which is the catchment just north of this. So if you imagine on the top of the geological map, this is Pine Island Glacier, the Bird and Bentley subglacial trenches just overlapping the top. And I'd worked out what the crustal thickness had been by inverting the gravity. So you could see that under the Bentley subglacial trench and Pine Island Glacier, you have really thin crust, about thinnest in 19 kilometers, about 19, 20 kilometers thick. And using this amount of thinning compared to the 35 kilometers up in the Ellsworth Mountains, we could calculate what the heat flux would be because we knew how much rifting had happened. But the problem that I came up against was it depended when rifting had happened. So in that top line where you've got Cretaceous rifting, what you end up with is the big deep basins where the crust has been thinned most are cooler and have lower geothermal heat flux than anywhere else. And the right-hand one shows the basal temperature. The model is not constraining the maximum basal temperature here. So the white outline shows where it would be melting if melting was allowed. If it was all recent rifting or Eocene or Oligocene 34 million years ago, everywhere the big basins has high geothermal heat flux. and you get much more melting due to the geothermal heat flux alone. And then in two-phase rifting, you get, a blend of these two patterns, but no dramatic change in geothermal heat flux. So my conclusion is kind of that Cretaceous rifting, which I think dominates Thwaites Glacier, isn't going to be driving high geothermal heat flux in this area. But there are lots of things that I'm not saying that doesn't have the high geothermal heat flux. There's lots of things that could be driving high heat flux in this area. Granite's enriched in radioactive elements, as seen in the Ellsworth Mountains. The mantle plume beneath Murray Birdland, which is seismically imaged. Active volcanism and associated flux of magma towards the surface. All of these things could be driving elevated geothermal heat flux. It's just that rifting and thinning of the crust due to Cretaceous rifting likely isn't driving elevated heat flux in this area. And also, one thing I wanted to note was I found looking at the tectonics of the conjugate margin really useful when writing the paper and trying to understand the geology. And I think using that conjugate as a maybe a better studied template of what and parallel to what was going in West Antarctica is quite a useful way to try and understand the region. So yes, thank you very much, and plenty of time for questions if you have any.
Thank you very much, Tom. That was really interesting. Yeah, if you have questions, you can raise your hand. I saw that some people already raised their hand and took them back. So I would have a question. Do you compare the roughness in the beginning with the sediment geological units? Are they all comparing to the other units, or you don't use it at all for the rest?
For the other units, I didn't see the granite seem to come up as rougher, and I think that's because they are forming these big highlands. But there wasn't a really strong correlation, like the signatures, like so within the highland, sort of feudal highland, the highly incised bit. I think there are parts that are probably granites and parts that probably aren't granites, but they're all showing up as incised highlands. They're all showing up as quite rough. So yeah, I only used the smoothness as an indicator of sediments, and the smoothness was the dominant indicator of sediments. So the gravity anomalies were sort of a supporting line of evidence, but the smoothness was the primary one, the primary line that I was using.
Okay, thank you. Lou has another question.
Hi.
We can't hear you.
I forget I muted myself. Great talk. I just wondering for your classification, there is lots of blank area. So do we have any sort of, what that type might be, or?
I was asked this by a reviewer, and I think my best and first estimate would be something like the Swanson Formation. So it's the highly metamorphic. So the whole region was a passive margin way back in the Cambrian. It was dumping lots of sediments into the ocean, the Paleopacific margin. Then that was all metamorphosed and folded and messed around. So I would think that Swanson Formation, and you get that exposed. I think that's my bet. With no other evidence, that would be my first estimate. Would be Swanson Formation. What we know is that it's not highly magnetic, and it's not got any particularly strong density contrast away from a background 2.67, which that Swanson would fit that bill, I think.
Yeah, cool. Can I keep asking? So I'm just curious, do you have any thought about how do we sort of move forward to use this geological information into something we can do in the numerical model, maybe in some way, to understand the influence of geology to the ice sheet, or how they change in the future?
Oh, this is the multi-million-dollar question, isn't it? How you
Yes.
how you blend those two. I think just understanding that there is that correlation with basal shear,
Mhm. Yeah.
and the geology, and trying to understand some of those steps in
Yeah.
basal shear
Mhm.
seem to be that are outside the sedimentary basins.
Yeah.
How you go about parameterizing a geological map into something that ice sheet model can use is a bit more of a tricky one. I mean, the first thing I guess would be you could look at permeability and say, okay, we think we've got sedimentary basins here. Let's just put in a block that's a kilometre thick with a permeability, and water can go in and out. And then we've got a block that we think doesn't have any permeability, so the water must be the ice bed interface. That would be something I think you could start to model how water moves through the system.
Mhm.
And then I guess it would be something about parameterizing basal shear stress.
Yeah. So do you think more about the friction coefficient or just basal shear stress or something like that?
I think trying to understand how much of the observed basal shear stress is kind of fixed and due to the geology, because at the moment when you do the basal shear stress calculation, it's everything we can't fit. This is my understanding of it. Everything we can't fit will cause variation in basal shear stress, and you then get ice velocity that matches the observed. Understanding how much of that is due to fixed geology that's long term, never going to change. You could change ice sheet configurations, you can do whatever. You'll always be slippery in this area because of the geology. Or in this area, we change the ice sheet configuration a bit, reroute some water. Actually, this basal shear stress that we're inverting for is a very transient feature. And it isn't going to be when we're modeling retreat in 500 years where it might have got back to those sedimentary basins. Are those sedimentary basins still going to be low shear stress? Or is that big block of high shear stress going to move? Is that high shear stress a function of where it is in the glacier, or is it a function of the geology? So I think that's where the geology might help. We need to start picking apart what basal shear stress is and what is fixed basal shear stress and what's dynamic basal shear stress. Not quite sure how you do it, but that's my thought of the next step. And that will be part of the parameterizing process.
Cool. Thank you. Well, should I keep talking? Go on.
So I don't see any other hands.
Well, I got a
Have
hand.
another question.
There we go.
I keep asking. So, you have some sort of granite in the upstream. So, do you see any sort of high basal melt or some sort of evidence because maybe some higher heat production to high heat flow in the area? Do you see any sort of correlation?
I've not looked.
Okay.
I don't know. I guess, we would have to look for things like drawdown of layers, but it gets a bit complicated because they are highlands. So they're shallower, therefore they'll be colder. So you need a higher. If the bed was flat and I was saying there was granite there, then maybe you could look for drawdown of layers. But because they're highlands, it might be a case of trying to look at some highlands and see if you find ones that you're really confident that's definitely granite, and ones actually we're pretty sure that isn't a granite, and then do a compare and contrast. Might be the way to look at it.
Yeah. Cool. And one last question. Okay. So if you calculate the geothermal heat flow, so do you assume that sort of which the starting heat flow you're given, like in the area?
Oh, for those calculations, that was, I think I basically I tuned them. I did those calculations back in 2009. So I I basically tuned it so it was 65, kind of a global average geothermal heat flux for this thick crust, about 65. Just using global average. The way the model worked was I just gave it a heat production and a like a lithospheric flux, and a crustal thickness, and then it worked forward from there.
Yeah, but the assumption is that we have sort of loss of heat from the crust, but the manual heat flow is got low in the area. Is that
I think that the scenario would be it's about 50-50. So at least half the heat flow is coming from the crust.
Yeah,
which
but
is
I think
why
from some like tomography model, they see the lithosphere is quite thin in the area. So like the lithosphere about 100 kilometers. So the manual heat flow can be quite high. So that the sort of high heat flow in the area.
Yeah, I mean that's what I was saying is I don't want to categorically say it's not high heat flow. It's just that that statement, it's a rift, it must be high heat. Doesn't always hold.
Yeah. Cool. Alrighty, thank you.
Thanks for your questions.
Yeah, I think Lou, you all asked all the questions that I had.
Oh, my bad.
Great. Oh, that's good. So maybe one last question, if no one else wants to ask. I would ask, do you expand this to other regions or to the continent-wide map, or is that not planned?
I think it would be really great to do. I think continuing this kind of generation of geophysical sketch maps it's the only way we can get at the subglacial geology. And I think there's a little bit of a reticence because it's always, but it's just geophysics. And we don't know because we haven't got the rocks in our hands. But I think it is the best we can do. And I think building up these sketch maps and understanding that they are geophysically derived, they are an interpretation. But it does let you have this view of what's under the geology and a bit under the ice in a bit more of a sensible way using the geophysics. So yes, I think definitely we should keep pushing to build this type of sketch map out across the continent.
Yep, definitely. Okay, thank you very much. Yeah, so I think if there's no other question, I would like to thank you, Tom, again, and thanks everyone for being a part of today's seminar. Our next seminar, we are still finalizing the details, but we will keep you informed through emails in the mailing list, so we will probably have another one in August. And yeah, so have a nice day, everyone, and thank you.
Yeah, thank you.
Bye-bye.
Yeah.